Hello and welcome back. Today we'll be getting into section 1.4 and 1.5. 1.4, we're just going to cover the polynomial part. The rational part we will cover when we do limits. So 1.4, again, abbreviated. We'll look at polynomial functions. So the basic setup for a polynomial function. F of x is a sub n, x to the n, plus a sub n minus 1, x to the n minus 1, a sub n minus 2, x to the n minus 2. And we keep going until we have a sub 1 x. Again, if you don't write it down, it's assumed to be an exponent of 1. And similarly, we finish off with a naught, x to the 0 power is worth 1, so assuming x is non-zero. So some rules for this: all a sub I are in the reals, and all of the exponents are in the set of whole numbers. So we are allowed to have a 0 power. A constant function is still technically considered a polynomial. And recall, n is also the degree of the polynomial. So our domain, set of all x such that x is in the set of real numbers. So you plug in any number you want for x, as long as it's in the set of reals, you'll get an output that is also a real number. Recall, this can also be written as negative infinity to infinity if you prefer the interval notation. And one nice property, particularly for our study with calculus, all polynomials are continuous everywhere. So every x value, we have continuity. A couple other nice properties. There are at most n zeros. X-intercepts. And there are at most n minus 1 turning points. So what we mean by a turning point, we'll just put ourselves in the xy plane here. If our function goes from increasing to decreasing, this would be an example of a turning point, or decreasing back to increasing. This is another example of a turning point. So just changes in what's happening to the outputs. Are they going from increasing to decreasing or decreasing to increasing? That would be then a turning point. And we have at most n minus 1 turning points. And we see that with our smaller trivial functions. For example, linear functions have 0 turning points and are degree 1. Quadratics will have exactly 1 turning point, and they are degree 2. Now I want to do a quick little review on the idea of parity. If our degree is odd for the leading coefficient of the polynomial, and a sub n is greater than 0, so a positive leading coefficient. Then in general, we'll be moving from Q3 to Q1. That's not to say that we won't spend some time in either Q2 or Q4, but overall, if we have a positive leading coefficient and an odd degree on the leading term, generally we're going to move from down here. Again, we might dip into quadrant 2 or into quadrant 4, but eventually we're turning around and heading far into Q1 and far into Q3 along the edges. That's what's referred to as the end behavior. If the leading coefficient is negative, we just flip the graph over, flip it about the x-axis, and then we're heading from Q2 into Q4. If, however, we have a polynomial and n is even, and again, we're going to stick with a sub n being positive leading coefficient, we might spend a good deal of time down here in Q3 and Q4, but on the ends, eventually, on the left side, we're going to be heading far into quadrant 2, on the right side into quadrant 1. So if we take a look at a sketch, and we don't even need scales on this, just a sketch, and we're told that this is a polynomial function, we can tell some key information about that polynomial. So if we know that this is the graph of some polynomial, by the end behavior, we're going from Q3 to Q1. We know that this is an odd degree. A sub n, our leading coefficient, is positive, greater than 0. And based on the number of turning points, I can tell a minimum degree. So here we have 1 turning point, 2 turning points, 3 turning points, 4 turning points. So our minimum degree is 5. Now, it's not necessarily only 5. It could be a 7th degree, a 9th degree, a 501st degree. We do know that it's an odd degree, and we do know that it's at least a 5th degree. It could be more. We don't know. But that's the bare minimum degree. I can't get this kind of shape from, for example, a cube. All right. So we have you all try a couple out. so those two are given as polynomials. See what you can tell me about them as far as parity, minimum degree, sign of the leading coefficient. Go ahead and pause the video, give them a try, and we'll finish them together. Okay, welcome back. So this first one, the end behavior, both are heading towards the same extreme, negative infinity. So this is an even. They're both heading down, so a sub n, the leading coefficient, is negative. Think of the graph of y equals x squared versus y equals negative x squared. So this one closer to that, negative. Now we can identify how many turning points we have, and that'll give us some information on the minimum degree here. So turning points 1, 2, 3, 4, 5, 6, and 7. So 7 turning points. So our minimum degree is 8. And then our last one, we're heading towards opposite extremes, positive infinity on one end, negative infinity on the other. So that tells me that n is odd. Because we're going from up to down, high to low, a sub n here also is a negative. And this time we only had 2 turning points identified, which tells me that our minimum degree is 3. So again, the rational functions, we'll be covering those when we go over limits. So those of you trying the My Math Lab authors homework, if you get a rational function, just kind of skip that problem. We're looking at the polynomial ones only in this section. Those of you that are doing the bookwork, 1.4, 1 to 22, all is what I would recommend. If you have questions, please get in touch. And let's see. Yeah, we'll put 1.5 on a separate file, but we'll cover them both in the same day. All right, so coming up, 1.5.